Hey everybody, this is Ryan. This is going to be a quick tutorial on the derivation of the backpropagation algorithm for VPN networks. And hopefully this will just be sort of a straightforward derivation using some typical transfer functions. We'll use the sigmoid transfer function, and I'm going to assume that you're familiar with differential calculus and all of the necessary requirements, as well as conceptually understanding what neural networks are all about. Okay, so here we go. We're going to go ahead and use the sigmoid transfer function because it's very, very nice. It's based on an exponential expression, as we can see here. It has some of the step-like qualities that we enjoy, that we need for the concept of a neural network, but is nice and smooth, which means we can do calculus on it. And it's in fact based on the exponential function, so it's going to be quite nice. So what we'll go ahead and do is compute the derivative of this, which we'll be able to just plug and play later when we need it. Okay, so this is the definition right here. Sigma of x is 1 over 1 plus e to the negative x. So let's go ahead and take the derivative. Direct substitution, right? d dx, 1 over 1 plus e to the negative x. By the quotient rule gives us this expression, e to the negative x over 1 plus e to the negative x squared, right? I'm going to go ahead and add and subtract 1 in the numerator here because I'd like to group these smartly. And you can in fact see here, ta-da, right there is how I want to group them. And I'm going to split this into two different fractions. Okay, 1 plus e to the negative x over 1 plus e to the negative x quantity squared. That's nice because one of those will cancel, minus 1 over the denominator, which was 1 plus e to the negative x squared. This term on the right here is the whole thing squared, right? Because 1 squared is 1. And this is nice because this right here is our original sigma, and so we can go ahead and cancel this first term here to give us just a sigma of x, and we'll rewrite this second term as sigma of x squared. And so sigma prime, we can go ahead and factor this, is sigma times 1 minus sigma. This expression is very easy and nice to sort of keep on tap. Okay, so we'll use this later. Given a neuron, right, this is sort of a diagram I'll use. Here, xi is the input to the neuron, omega is the weight that connects that input to the neuron, sigma is the transfer function that we're going to use for this neuron, and script O is going to be the output. Okay. Here is the equation which defines the output of this neuron. Script O is sigma of xi omega. And this is just about as simple as it can get. Now typically, if you recall, hopefully from your research, for step functions we really are concerned with a threshold, and there is something analogous to the threshold for the sigmoid function, which is typically, and in mine presentation here, certainly denoted with theta. Okay, so if we include a bias term theta, the equation defining the output of a single input neuron is going to be like so. Script O is sigma of xi omega plus theta, where theta is the bias term, xi is the input, and omega is the weight connecting that input to this neuron. Okay. Now realistically, there can be several inputs to the neuron, and here's a diagram of that. Now to compute the output of a neuron in this instance, we're going to do sort of the intuitive thing. We're going to look at the input from whatever, input 1, multiplied by the weight that connects it to the neuron, as you can see here. We're going to add it to the product of the input from wherever our second source is, times the weight that connects that source to this node, and the same for the third. Okay, we're going to go ahead and add all of those up, and again, we have our theta, our bias term, which appears right here. Once all of those are multiplied together and added up, we're going to go ahead and plug them into our transfer function, which in our case is going to be the sigmoid, which gives us our output. Okay, script O is given as this equation right here. Now, to make a network, we're going to put a lot of these neurons together in parallel and form a layer, right, just like this. And we're going to put multiple layers together to form a network, like this. Okay, this is an example of a neural network, fully connected, which we will treat them all as fully connected. And in this case, this has one input layer, one hidden layer, and one output layer. Okay. The input layer boxes are gray and square because they are not passed through the transfer function. They are simply a buffer to hold whatever our raw input values are. Okay, so if we were going to compute the output of a network like this, we would plug in our values here, multiply them by whatever weights it is that connects them to the nodes in the next layer, add those all up, plus the bias term, pass it through the transfer function, and that's our output. And then we would continue by passing that output multiplied by these connective weights here, add them all up, plus the bias term, which is going to give us our output after passing it through the transfer function. Now, the notation that I'm going to use, and I will refer to these layers in this particular example as, is IJK. Okay? These are capital I, capital J, capital K, excuse me, where capital I refers to the input layer, capital J is the one hidden layer in this network, and capital K is the output layer. All right? So we're going to need some notation, so we can go ahead and develop this backpropagation algorithm. We're going to use x sub j to be the input to the jth node of the layer that we're concerned with, which I use upper L, script L, to denote. Capital W sub ij is going to be the weight from the previous layer, node number I, to the current layer, node number j. Okay? Sigma, for our purposes, we're just going to use the sigmoid transfer function. This we can actually turn into something else later, which we will do when we develop our network library. But for now, we'll just use the sigma we've been concerned with. Theta sub j is, as you would expect, the bias of the jth node in the layer that we're concerned with right now. And script O sub j will be the output of the jth node in the layer that we're looking at. T sub j is going to be the target value for the jth node of an output layer, right? Because what I'm going to do is provide an input, compute the output, tell it what I want the output to be, these T sub j values, and then use the difference between those to compute a delta, and I'm going to propagate that delta backwards through the network to adjust it and train it. All right? So this is the notation. Now the error calculation is given like this. So let's assume that we have a set of data points, T sub j, which is our training data, and the output layer output, script O sub j, right? We can write down the error equation like this. E equals 1/2 the sum across all nodes in the output layer of the output minus the target value quantity squared. Oh, there is a problem here. These are supposed to be sub k's. Sorry, this is a j. Should be a k, because we're looking at an output layer. And what we're going to do is we're going to calculate the rate of change of the error with respect to the weight sub jk that we're concerned with, and we're going to use that to do essentially gradient descent on the gradient of this expression with respect to the weights, and we're going to propagate that backwards through the network and adjust it as so. Okay? So now there's two cases to consider. The weight is either going to be a weight for a hidden layer, or it's going to be a weight for an output layer, right? Because there's no weights involved in the input layer, that's just a buffer. Okay, so now we're going to consider both distinct cases. First, where it's an output node, second, where it's a hidden layer node. All right, so here we go. For the output layer nodes, we're going to want to compute the derivative of error with respect to the weight from j to k, right? Where here little j is a element of the hidden layer capital J, little k is a element of the output layer capital K. All right, so this is the derivative of the error expression, which is right here. Here I do have the k's incorrectly, sorry about that. With respect to the weight from j to k. All right, so let's go ahead and compute this. We're going to do the chain rule here, right? Derivative of the sum is the sum of the derivative. We're going to bring this 2 out with the power rule. It's going to cancel the 1/2. We're going to get this internal expression, output of k minus target value of k, times the derivative of the inside, right? Now t sub k is a constant, which that means is going to go to 0, and so we're going to look at the derivative with respect to the weight from j to k of the output of k, right? There's that first term. Here's this last part. Now the output of k is really just our transfer function evaluated at the input to k, right, which was x sub k. Here I'm suppressing the upper L's because they're just going to get in the way. Now I know the derivative of the sigmoid transfer function because we did that earlier. That's just sigma times 1 minus sigma. So we can go ahead and do this by the chain rule times the derivative of the inside. All right, so here's our sigma of input times 1 minus sigma of input is times the derivative, sorry, of the input itself, right, by the chain rule. Oh, one thing to note, you notice that the sum went away because I'm abusing notation here a little bit. Little script k in this expression is allowed to vary over the entire output layer, but capital W sub jk is a specific weight connecting the jth node to the kth node in the hidden and output layers respectively. So everything that isn't actually connected to this weight doesn't vary as this weight changes, and so its derivative is 0, which is why that sum disappears. Sorry, I should have mentioned that. Alright, so let's look at this derivative right here with respect to the weight from j to k of x sub k. Now, x sub k is just the output of the jth node, right, times the weight from j to k. And so the derivative with respect to the weight from j to k of the product output of j times weight from j to k is simply the output of j, right, which you see here. And sigma evaluated at its input is just the output of the node. So that I'm just going to go ahead and simplify like this. Okay. Now for notation purposes, I will define delta sub k to be the expression above, which is going to be the collection of all of the terms here which involve the subscript k. So that is going to be output of k minus target value of k times output of k times 1 minus output of k, which is really just the derivative of the transfer function. Okay? So referring to this expression as delta sub k, we can rewrite the error with respect to the weight from j to k like so, right? Derivative of error with respect to the weight from j to k is equal to the output of j times delta sub k, okay, where delta sub k is all of the terms in this expression right here which involve subscript k. All right, so that's delta k and how the weight affects the error if this is in the output layer, because, right, this involves this t sub k value here, which is in fact what we desire our network to output, and we will use this to propagate the error backwards as we move forward. Okay?